Hello everyone, welcome back to my channel. Today we are going to deal with a integrated rate equation for a first order reaction. In our previous video we dealt with zeroth order reaction, and I hope everyone, those who are watching this video, have watched that previous video so that you will get a good understanding, or you will remember how to differentiate between first order and zeroth order reaction. Now moving forward with this derivation, let me state the question. The question is as follows: derive integrated rate equation for a first order reaction, or it may be stated as derive integrated rate equation for the rate constant of first order reaction, or it is also be stated as derive integrated rate equation for a velocity constant of a first order reaction. Now moving to the solution. For step 1, we need to consider a first order reaction. Why? Because we are deriving it for a first order reaction as stated in the question. We must consider a first order reaction. We know in any reaction the reactants with respect to time will give you product. Now we have R as reactants, P as product, and with respect to time it will give products. From the rate law we know that in first order reaction, the rate is directly proportional to the first power of, that is the to the power 1 of reactant concentration. Therefore, according to this statement, this is from rate law, we have rate is directly proportional to the reactant concentration. This big bracket R represents the reactant concentration to the power 1. This is not bracket R dash, this represents the reactant concentration R to the power 1. Now removing this proportionality constant will give you rate equal to K concentration to the power 1. Now what is this K? This K is nothing but where K is a rate or velocity constant. But we know that rate is nothing but a negative sign represents the decrease in the amount of the quantity. Here with respect to time, after conversion, rate will slowly or gradually convert into product. So after conversion there will be no reactants, or the amount of the reactants is low when compared to the amount of the product. So the negative sign is taken because the reactant concentration or the amount of reactant is decreasing with respect to time. This represents the differentiation of reactant concentration with respect to time, and the negative sign represents it is decreasing. So this implies that minus d of big bracket R, that is the reactant concentration, to the dt, this is equal to K of reactant concentration as we stated in the above statement. This take as this we are going to take as a equation 1. Now on rearranging the equation, the rearranging is very simple. Take this dt to opposite side and the reactant concentration to the denominator, and even take the sign to the opposite side. And hope this is easy, as you are well with mathematics. Now integrate the above equation. The second equation is integrated. Always remember, before the integration you need to make sure that this dt is sent to other side, and the term which is there in this d, inside this d, is also be present in the denominator. Why we do this process is because the integration of this kind of terms will give you ln of the term, that is here the term is into reactant concentration. Therefore we will rearrange such that dt will go other side, and the term which is inside this d will be in the denominator. D of reactant concentration in the denominator, reactant concentration, will give you negative K dt. Now integrating the above equation, this is nothing but we have taken a integration symbol. This will give you ln of R. As I told you, we are rearranging. Why? Because we will get a ln, which is which is a simplest or simple method to solve this type of terms using a ln or a log. So this gives you negative of kt plus I, as we know that I is nothing but an integration constant. We know if we integrate any term, we will get a constant c, or any term. Here we are taking that as a I. Now we should know what the value of I, or what the I is. So to know, in order to know the I value, we will take this equation such that we know this value, we should know this value, and this both the values along with this value, so that on equating we will get I value. Now the only time which we can consider this two and this term and this two term is when t is equal to 0. When this t is equal to 0, the time in which the product is not yet formed, the reaction is just started, not even started, about to start, is t is equal to 0, and the time at which the reactant concentration is R0, where R0 is the initial concentration of the reactant. At that time and at that concentration, we have ln of R0 is equal to minus k into nothing but equating this, substituting these values in this equation 3 will give you the value I as ln of R0. Now we consider the time in which we know this value and this value, so that with that help and with the help of this third equation, we found the value of I. Now substituting the value of I in the equation 3. Now we want to know what is the k value. We found I value from these two initial conditions. Now we substitute this I in the equation 3, so that on rearranging we will get the k value. Moving further, now I rearranged. Now on rearranging we will get ln R is equal to minus kt plus ln R0. Now take this term to LHS. That gives kt is equal to ln R0 minus ln R. kt is equal to ln R0 divided by R. This is from the property of ln, or if you know log, the same thing is also applied in the log property. Log a minus log b is nothing but log a by b. The thing is applied here. Now kt is equal to 2.303 log to the base 10 of R0 by R. You know the conversion factor is 2.303 from ln to log. Always remember the conversion factor is 2.303. We just converted from ln to log. Kt is equal to the given thing. Now k is equal to, just take this t to RHS. K is equal to 2.303 by t log to the base 10 R0 by R. What we got? We got the constant. The constant is nothing but the rate law constant of first order reaction, or velocity constant. Now as above equation, from this we can do that ln R is equal to minus kt plus ln R0. Now comparing this same equation with y is equal to mx plus c. You know this is the equation of a straight line. Now as you all know, m represents the slope of our equation. On comparing these two, we will get m is equal to minus k, which represents that negative of the given constant is a slope of a graph, when y is ln R and x is time. Now we can see the graph here. Just compare these two terms. There is nothing you need to remember, or nothing else you are supposed to do here. Just comparing, you will get y, you will get x, we will get slope, everything. This will be helpful for your CET or any competitive exams. You can just need not to remember everything. Y is nothing but a ln R. Comparing, you will get y is equal to ln R. State, plot y, m is equal to negative of k, that is a slope. Plot slope here, and x is t. And you know this term represents the interception in the y axis, that's ln R0. Intercept is nothing but a ln R0. Now this is ln R with respect to time. Now from this we can also represent log to the base 10 of this with respect to time. That gives you slope as k divided by 2.303. Take this to that side, will give that slope. Now the important note here, as we came to the last part of our derivation, the important note is the slope of the graph is negative, but the rate constant is always positive. Always remember that slope is only negative, but the rate constant value is always positive. Now, you know that there are two types of graph here. You need to be very careful and sensitive while considering the graph for the given question. Always prefer these graphs in your derivation. And if you are thorough and confident that I know this graph is exact what I remember, then only write this graph. Always do prefer to write this graph. Now, we took our time to explain you the concepts which you are studying. So just take a minute to share the video to your friends and take a minute to like, even subscribe our channel. Thank you.